What if the cleanest fuel on Earth could lift a helicopter, power a data center, and protect a nation all at once? At HYSKY Society, we're turning that question into reality. Our mission is to connect the pioneers using hydrogen to solve the world's hardest energy problems, whether that's flying further, powering AI, or reaching the front lines. We do this through key programs like HYSKY Monthly, where we highlight global experts in hydrogen flight, and Flying High, the top hydrogen aviation event, or HYSKY EDU, with courses like hydrogen aircraft design, and HYSKY Connect, a fast-growing platform linking hundreds of hydrogen innovators. At HYSKY Society, we believe in clean energy abundance, and hydrogen, the most abundant molecule in the universe, is key to unlocking it. So, we're sharing this pivotal research in order to deploy these innovative technologies across the world. Think aircraft that fly hundreds of miles with zero emissions. Think clean energy for AI data centers. Think drones with the range to reach targets far behind the front line. Hydrogen isn't theoretical. It's happening now, and HYSKY Society is where it all comes together. Welcome to HYSKY.
Now we'll do one more video, a couple more videos, and then we'll get into some of the surprises that I promised.
Meet the leading women of hydrogen aviation. These women are changing the way we fly and saving our skies. Meet them all at Flying High.
So speaking of Flying High, let me just quickly show you. Flying High is less than a month away. It is coming up right around the corner, November 5th. And you can just go on to our homepage, hysky.org, to register. Tickets are $30, so it's practically free for students. And you just hit this register now. But as I was saying this morning, the AWS thing has kind of messed us up, so it may take forever to load, but hopefully that will be straightened out by the end of today, hopefully by the end of the hour. And then I just quickly want to show you all this new course that we're launching. So we just recently concluded the H2 aircraft certification course, and we had a lot of requests for the hydrogen fire safety course. So this course starts December 2nd. It is $500 to join, 3 weeks, 6 classes, 12 total hours. And if you're a VIP member, you can get the course for $200. So highly recommend this one. We're going to cover loads of things, and I'll stick this link in the chat so that you can go ahead and check it out, read more about it in your free time. And yeah, I can skip that one. Okay, so now I want to show you this company, which was kind enough to invite HYSKY Society to their live flight demo this morning. Unfortunately, we couldn't make it in person, so we had planned to live stream it and show you guys their flight. But again, because of the AWS stuff, we could not get it coordinated. However, we did get some videos. So these just happened. So you all will be the first to see these videos. So let me just get it pulled up. And they were done on a phone, so the quality is not the best, but you're seeing it here first. So here's the takeoff. And then here's another one. So you can see how quiet it is. I mean, you didn't really hear it until it gets really close. So yeah, congrats to Air Vive. They're an Israeli company, and this was in Florida that they did this morning. So very exciting. I wanted to be there in person. I was hoping we were going to catch the CEO's presentation, but the internet lords decided not to today. So now I am so excited to introduce you all to our speaker today, Nicolò Baiguini. Nicolò is a chemical engineer at Politecnico di Milano since 2018, a PhD in energy and process at Mainz Paris Tech University, PSL since 2023, with a thesis on modeling of cryogenic liquids in small scale tanks. He leads the hydrogen project at DTC since 2024. So now it is my pleasure to pass the stage over to Nicolò. Nicolò, the stage is all yours.
Danielle, thank you very much. Good morning to everyone. Let me share my presentation. Just 1 second.
Yep.
Can you see my presentation?
Yeah, you'll want to go into presentation mode, but yes, okay, perfect. You're good.
Perfect. Okay. Thank you very much. Okay. Today I will present the EICLHAIR project, which is the development of a liquid hydrogen tank and fuel system for aviation. My presentation is divided into 5 parts: an introduction, the explanation of liquid hydrogen behavior, the storage tank, the fuel system, and the conclusion of this project. Now, let's start with the introduction, where I present the context, the state of the art, the difference and the choice of the internal combustion engine instead of fuel cell, and the description of the project itself. Now, as you can see on the left, my left, there is a image showing the direct and indirect CO2 emission for a sector in 2010. As you can see, transport accounts for 14% of the carbon dioxide emission, direct carbon dioxide emission, but at least zero for the indirect. And the main source of carbon dioxide emission are electricity and heat power, agriculture and forestal and other land use, and industry. But if we look at these 14%, we can see that at least in Europe, the aviation accounts for the 4.6% of the carbon dioxide emission, and the road remain the main source of carbon dioxide emission with at least 20%. So aviation is the lowest source of the carbon dioxide emission, but at least is the one that is we will try to reduce as much as we can our emission, because it's something that the people really take about it. How we can reduce the emission from the aviation? First of all, we would like to reduce the on-ground time when the engine runs without moving the plane. Optimization of the flight path to reduce the distance between the point A and point B. Increasing the energy efficiency of the engine, and for sure using fuel that do not produce carbon dioxide, such as hydrogen, or at least they have neutral CO2 production. That means that they are fuel produced from green, from captured CO2, or from biogas or biomass. Now, if you look at the property of the different fuels, such as JA, hydrogen at 700 bar, and liquid hydrogen, and suitable aviation fuel, we can see that the heating value of the hydrogen is the highest among is higher than jet E and SAF. Nevertheless, the heating value per unit of volume of hydrogen is lower than the standard aircraft fuel, and in particular, liquid hydrogen is better than compressed hydrogen on terms of storing energy per unit of volume. If you look at the price, you can see that the SAF are much expensive than hydrogen, which is more expensive than GA. Why SAF is more expensive? For the simple reason that we need to produce hydrogen first, then capture carbon dioxide, and then synthesize the fuel, instead of using hydrogen where we just need to liquefy for producing liquid hydrogen. Now, anyway, one of the main drawbacks of using hydrogen that we need to rethink the power unit and the storage system. On the other hand, if we use SAF, we can use almost the same storage and power system. Now, you have seen that, so liquid hydrogen seem among these all the fuel seem a very good fuel for the aviation. Now, the light aircraft, drone, and ultralight motorized vehicle, they all belong to the category of the light aviation. And usually the light aviation run on a sparkling gasoline engine, and the average age of the fleet is around 45 years. Now we need to reduce the carbon dioxide emission and to create a sustainable light aviation. We need to retrofit the fleet. So how we do that? We like to reduce the use of fossil fuel, reduce the noise, and enhancing the economic industrial sovereignty or where these aircraft are done. Now, to do that, we have, of course, developing a new storage system, a new power unit, and developing new concept of integration. If you look at how the hydrogen is stored on aircraft, usually there are is storage at 700 bar, or as a cryogenic liquid at minus 153 Celsius. Now, using compressed hydrogen gas is the main use on the sustainable light aircraft, because is easy to install and to run, and the storage technology already existing on almost large scale, as you can see by this tank. There's this composite tank that is produced by NPROX. There are many ongoing projects like Project Fressus and the project that is developed by ZeroAvia. On the other side, the liquid hydrogen storage can guarantee higher gravimetric index, whose value is around 11-13%. But the storage technology is more complex, and the technology is still on developing. Here, an example of a storage technology from Mania, which is a liquid hydrogen tank. The thing that they use for aircraft, but they are still prototypes. They are not at the same level the gas technology. Concerning the liquid hydrogen project, there are so many interesting state cases. One of them is the EVEN project. It is a project carried by the consortium HYSKY, which is composed by Air Liquide, Pipistrel, DLR, Expo, and ASIA. Pipistrel is this aircraft that is shown here. This is images taken from flight test. The aim of this project is develop a liquid hydrogen tank to run a fuel cell, which can guarantee at least 1,500 kilometers of range of flight. This is the tank that is manufactured by Air Liquide. As you can see, it's stainless steel. With this part is the vessel with liquid hydrogen. This part is the box valve. This tank is based on the following process diagram that is reported here. We have an heater to maintain the pressure in case of the pressurization of the tank. The liquid hydrogen is extracted by simply the difference of pressure between the tank and the fuel cell. And in case of over-pressurization, there is a boil of gas and a relief device that reduces the pressure in the tank. An heat exchanger is present to convert liquid hydrogen into gas. Well, this kind of technology did not overcome the value of 11% of government index. Another project is carried by Aviation, which is developing today, is developing a liquid hydrogen tank for a fuel system for sport car. Why we talk about sport car? Because it's very similar to the fuel system and the power unit of a light aircraft. This is the if you see on the left, you can see the cross view section of the tank. You can clearly see the support, the gas and liquid pipe. The box valve you can really not see, but it is here. And in this image, we can see the type of insulation, thermal insulation that they're using is a MLE, so multi-layer thermal insulation. However, the fuel system is completely different from the previous one. They are using 3 buffer tank to make an isochoric compression. In the first tank, the liquid hydrogen is charged. In the second tank, this liquid hydrogen is converted into gas by using an LH2 exchanger. And in the third buffer tank is working to deliver the hydrogen to the system. Another interesting, even if this project is developed for a sport car, as I said before, it's very interesting for light aviation, is the case of Toyota GR Corolla H2, where they have developed a liquid hydrogen tank and fuel system for a spark engine. The manufacturer tank is the one that is manufactured by Ube Chico company, and in this report in this minute here, we can see that the cross section is oval and they're manufacturing the tanks in aluminum. Why did they use this type of cross section? Because they can increase the volume tank to volume occupied ratio, which allows them to store something like 15 kilograms of liquid hydrogen. The fuel system is different, as it is reported in this image. You have a buffer tank, a pumps, a catalyst to convert the ball of gas, and an exhaust gas heat exchanger. This image here is just to give you an idea of how it looks like this Toyota GR. Now let's move. As we can see, most of the projects are using fuel cell. What is a fuel cell? Is simply a battery. It's like a battery where you convert hydrogen and oxygen into water by directly producing energy. Electricity. Now, usually an example of fuel cells is reported in this image of the Toyota fuel cell stock that is currently used on Mirai, I think. However, the installed power density of the technology is around 2.2 kilogram per kilowatt of energy produced, which is quite high respect to this value of the properties for the internal combustion engine. Today, light aviation usually uses this type of technology, as reported in this image, the Vortex 912 IS, whose installed power density is around 0.8. Anyway, using a sparkling engine has some drawbacks: NOx production, noise, vibration, but they are based on common materials such as iron, aluminum, which are easily available on the market. Hydrogen sparkling engines are very similar to the existing gasoline engine, so it allows easily maintenance, contrary to fuel cell, which is actually a brand new technology. There's not so many maintenance knowledge around the world, and they need expensive material. Of course, a fuel battery do not produce pollutant and are more efficient. Now, if we consider the advantages of use internal combustion engine and the storage of liquid hydrogen, we came up with the EICLHAIR project, which is the development of liquid hydrogen tank and fuel system for a sparkling engine which run on hydrogen. Now, the project is divided in 3 parts. One block is the developing on the engine, the other is the storage tank, and the last feature of the project is installing the technology on an existing aircraft. Why an existing aircraft? We want to prove that we can convert existing gasoline aircraft into hydrogen aircraft. Now, the engine is a 2 liters inline 4-cylinder, usually which works with air to fuel ratio above 2. Why we have chosen this value? To avoid the formation of NOx, as reported in this graph, which shows the equivalent ratio and the NOx production. If we use an equivalent ratio that is very low, so a lot of air in the cylinder, we reduce the NOx formation. The maximum takeoff power of these engines is around 150 kilowatt, and we expect to have a power density of around 0.5 kilogram per kilowatt produced. The storage tank, there are 2 prototypes of the tank. The first prototype is made of composite and aluminum. Composite is used for the vacuum jacket and aluminum for the internal tank. And the second prototype will be made with 100% of composite inner and external jacket. The gravimetric index that we expect to have is around 30, 35, and 45. Why we want to stay above 35? Because if we are below, the liquid hydrogen storage is less efficient than the storage of the current jet fuel. Now, another main part of this project is installing. What does it mean installing this technology? It means adapting the airframe, so doing some modification on the airframe of the aircraft, handling and managing the liquid hydrogen on board and on ground. The filling procedure, so how do we fill the liquid hydrogen in the tank? How do we extract the gas? And of course, all these things must be done respecting assuring safety. Now, this project is sustained by BP France, which is an investment bank, and sustained by the French government economic plans called France 2030. This project is carried by a consortium made by 3 societies, EHP2, DTC, which is Design Tech Center, and IC Group. EHP2 is the leader project, and they are, and this society is engine design since 2018. They have a lot of the experience come from sport, from Peugeot Sport, GP2, and the Airbus helicopter. We, as a design tech center, we developed the fuel system liquid hydrogen tank. This society was born in 2005, and since 2017, we work on the hydrogen tanks. We are a million engineering office, and the last partner of this project is IC Group, which the aircraft manufacturer. They produce the ICDs, which are light aircraft that can be convertible to drone. They are producing this aircraft since 2012, and they are in charge of onboard tests, installing, and maintenance. Now, let's move on how liquid hydrogen behaves. Now, this part is divided. In this part, I will present what is liquid hydrogen, how it behaves, and the heat transfer that we have in the storage tank, the evaporation, the main phenomena that can occur when we close the tank, and dissolution. Now, we usually say hydrogen, but we should say dihydrogen, because dihydrogen is a molecule formed by 2 atoms of hydrogen. It's a permanent gas under standard condition, which means it can be liquefied by simple compression. We have to decrease the temperature to minus 250 degrees Celsius if we want to liquefy it. There are 2 isomers of hydrogen, which are the para and ortho isomer. The difference is just the number of spin. In ortho, both number of spin have the same number of spin, which means that the atoms rotate in the same direction, roughly speaking. In the case of para, it's different. The direction of rotation is or inverted. Now, if you look at this graph, which show the conversion of ortho to para at equilibrium, we can see that below 75 Kelvin, the para isomer is more stable than ortho. The reaction of conversion from ortho to para is isotherm, so we have to do this conversion before storing the liquid hydrogen. Otherwise, the isothermic reaction will produce excessive boil of gas. Now, what is the liquid hydrogen behavior? Roughly speaking, is the variation of pressure, temperature, and filling ratio over time. The variation of this variable depends on three main phenomena: evaporation, thermostratification, and self-pressurization. These phenomena are affected by different variables such as the operating condition. For example, if we open, we close the boil of valve, or if a tank is moving or not, as indicated in this image, where the tank move as indicated in the orange arrow. Depending on the weather conditions, there is sun, wind, so the temperature is cold, it's hot, it's a summer day. And of course, it depends on the design parameters such as input geometry and maximum operative pressure of the tank. So how this variable change in times. Now, they change as function, mainly as function of the heat inputs on the tank. So how the heat moves from the outside to the inside of the tank. Now, why do we have heat inputs? Because there is a very large temperature difference between the outside and the inside. Inside, we have minus 253. Outside, there are temperatures ranging from minus 10 to up to 70 degrees Celsius. So it will pass from the wall, as indicated here, will pass from the support, from the pipes, and will be instrumentation, if we have some instrumentation inside, and it will have some heat coming from pumps that can be installed in the tanks. Now, this heat cannot be removed. We always have heat inputs in the tank. Now, the heat from pipes, support and instrumentation is roughly transferred by conduction, which means that depend on thermal conductivity material and on the surface of contact and temperature gradient. Now, the heat that comes from the pumps depend on the efficiency of the pump. Less is the efficiency, more is the heat that is given to the liquid. But the heat transferred from the wall, that depend on how we design the thermal insulation. Now, how usually the heat that moves from the outside to the inside through the walls depend on different steps. Now, firstly, the heat must be flow from the air to the external wall, then pass through the insulation, and then move to the internal wall. When the heat arrives at the internal wall, the heat moves to the liquid or to the gas. Now, the heat along all this pathway remains always constant. The heat that moves from the external to the outside to the external wall may depend on radiation. For example, if there is it's a sunny day, radiation from the sun will increase the heat input. Or if there is wind, we may have forced convection that transfer more heat to the vessel. The heat that is transferred into the insulation mainly depend on the radiation and conduction. So if you use, for example, vacuum and MLE, the heat will mainly transferred by radiation. If, for example, use foam, the heat will be transferred more by conduction. At the end, the heat that is transferred from the wall to the fluid depends on the convection, so how the liquid moves inside the tank. Now, this heat inputs cause a permanent evaporation of the liquid hydrogen, as we can see from this picture. The mechanism of evaporation depends on the natural convection of the liquid, which and usually, if the tank is open, the liquid inside here remain homogeneous, and all the heat that is absorbed by the liquid through the wall is released by the evaporation, so the temperature remains constant. But the ullage is thermally stratified due to the heat impulse that come in, and because there is not enough natural convection to keep the temperature homogeneous. Now, we can roughly say that all the heat that comes from the environment is converted in evaporation heat. and this evaporation heat depend on the pressure that they're working on. If we increase the working pressure, the latent heat of evaporation reduces, so which actually increase the evaporation rate. So when we are in a very small tank, for example, on light aviation, we cannot allow the boil of gas to exit the tank because we don't know what we do with this boil of gas. So usually we close the tank, but by closing the tank, we increase the amount of heat and mass that is trapped in the ullage. We actually increase the pressure. This increment of the pressure is what we call self-pressurization. Now, as we pressurize the tank, the amount of liquid that is warm start to accumulate at the interface, as it reported in this imaging here. So as more warm liquid accumulate at the interface, more we partially increase the pressurization rate of the tank. At the same time, this stratified region increase by time, as it is reported in this imaging, and it is stabilized and stabilized, creating two separate regions, a stratified region and an homogeneous one. Due to this thermal stratification, the self-pressurization is enhanced, as we can see here, some curves, some experimental points from NASA indicating how the pressure increased by on times. If the starting point is a completely homogeneous temperature in the temp, so the temperature is completely isothermal, the boil of gas is lighting higher than the one you will have if the tank is at its minimum point of energy, so it's homogeneous, the temperature is stable. As we reduce the filling ratio, we should expect a reduction of the pressurization rate. That's what we see when we move from 75 to 50%, because we increase a lot of the cross-section area of the tank. But when we move from 50 to 35, we don't have the same trend. We have an increment of the pressurization rate for the same reason, because we reduce, in that case, the surface area, and we reduce the way the heat is transferred between the surface. Now, sloshing is another important phenomenon that can occur on a light aircraft, because the tank is moving. It may be stopped when if the tank stops when it is landing, the liquid moves. So if the tank is open, we expect that the liquid will climb on the surface, and the hot surface will be quickly cool down, creating an excessive production of boiler gas. It's as most instantaneous, it does not really impact the system. But if the tank is closed, as we said before, to avoid boil of gas, in that case, the sloshing will cause a rapidly drop on pressures, as it is here reported in this graph, which show the pressure variation in the liquid nitrogen tank. Now, the first part, as you can see, is a self-pressurization, and at this time here, the sloshing is applied. As you can see that the pressure rapidly decreases, and this reduction of pressure is caused by the fact that the liquid is more exposed to the gas, which actually is very cold, is cooler than the pressure of the tank, which by consequence reduce the pressure. Now let's move on how we have designed the tank and how we which is our approach on designing the tank. On this part, I will present the architecture of the tank, the rules that we used, the operating pressure, how the mass has been optimized. We have chosen the shape of the tank, as we have designed the thermal insulation, and the system of controlling the pressure. Now, this is an example of a liquid hydrogen tank that is being developed by Linde. As we can see, the vessel is made by an external tank, outer vessel, an inner vessel. Both are separated by thermal insulation. There are a filling port, gas extraction pipe, filling line, heat exchanger, so in this case, electrical heater, safety valve, shut-off valve to cut to avoid that the liquid nitrogen goes to the fuel system, and heat exchanger to convert liquid hydrogen to gas, suspension to keep the inner vessel attached to the external. We may have other additional functions that are not reported here, for example, such as fuel dump line, return gas line for the pressurization, inner pumps, and eventually after this to about brake pressure if it is too high. On general, cryogenic vessel or liquid nitrogen vessel are made of inner and outer vessel, separated by with a thermal insulation, usually is a MLE. There are suspension and valves and pipe to control the gas and liquid flow. Now, if you look at the rules, there are some ISO standard concerning the designing of pressurized cryogenic vessel for land vehicles, large transportable cryogenic vessel, and some of these ISO standard also define the materials that can be used for liquid hydrogen tanks. But these ISO standard do not respond to the question on case of crash, the safety and the design criteria, for example, safety coefficient, welding coefficient for an aircraft. On the other hand, there are the CS23 rules that are used in Europe for the certification of aircraft. And of course, for the power and fuel tank, for unit of fuel tanks, usually this rule defines the test that the tank has to be submitted, the integration constraint, how to design the filling port, how to define the flow rate for design the fuel system, the independency of the pumps, how to avoid, how to protect this technology from, for example, lighting. But this rule do not answer to the question if you use a liquid hydrogen tank as well, do not respond to the question how to handle the boil of gas, what is the maximum operating pressure of the vessel, and which type of this thermal insulation can be used, for example. So we don't have really a rules to follow to design cryogenic tanks for liquid hydrogen tanks for aviation. So how we do it? We have started by looking at the operative pressure. There are two operative pressures, the maximum and the minimum. So the minimum pressure must be above 1 atmosphere to avoid air leakage in the tank, but the maximum operative pressure depends on the geometrical form, material of the tanks, and all the neck time and its inputs. Now, if we would like to the mass and this operative pressure directly affect the mass of the tank, which is composed by the mass of liquid hydrogen, the mass of the insulation, the mass of the support, and the mass of the inner vessel, the mass of the jacket. So the mass of the liquid hydrogen that we carry inside is the mass of the liquid hydrogen that is lost in evaporation, the mass of the useless fuel, and the mass that must be kept inside as a heat. Now, if we increase a lot the thermal insulation, we can minimize the hydrogen that is lost by evaporation, but we increase the mass. On the other hand, if we reduce at the minimum required value thermal insulation, we increase a lot. We can use a lot of hydrogen by evaporation, and if we increase the ordinary type as reported here, we simply increase the thickness of the wall, which increase the mass. So it seems that we have a problem of optimization of thermal thickness, as the reporting here in this graph that is being done by NASA on 8.5 spherical tanks of liquid hydrogen. We clearly see that the mass, which is the purple line, is a minimum of at around this value that is around 7 inches. Why there is a minimum? Because as we can see, the storage mass of liquid hydrogen is reduced with the increment of the thickness of the insulation. At the same time, the increment of the thickness increases the mass. So at a certain time, the gain on liquid hydrogen is lost because we increase too much the mass of the insulation. So we do the same. We're trying to figure out what is the minimum of our system. Now, we also have to reduce the mass of the wall. And in this case, if we increase the pressure, of course, the mass of the linear vessel will increase. As it is reported in this graph, the increment is almost linear. At the same time, the evaporating mass of the hydrogen tank increases with the storage pressure and maximum operative pressure. Why this? Because we reduce the latent heat of the liquid hydrogen, which means that we need more mass to be evaporated to absorb the same amount of heat. So actually, it suggests that we have to stay as low as we can on the maximum operative pressure. Now, the shape of the tank, if we look how the aircraft are made for aircraft, you can see that they are placed on the wing and in the center of the tank. Of the aircraft is reported here by, you can see for the Boeing fuel tank of the 787. As we can see, the form of the tank are, roughly speaking, cuboid or parallelepipedic. And we may think that if we have to design the shape of the tank, we have tried to fit a sphere in a cube or a cylinder. But between, if you want to use sphere or cylinder, it's better to use cylinders. As we put here, the volume to tank volume to occupied volume ratio is higher. But actually, this is not the way you should approach. If you look at this image, the cross-section geometry of aircraft is not a cube. It's a circle, for example, here, an ellipse here. So the problem is how we can fit a tank in a circular sector. Circular sector just is the green part here, which actually corresponds to that part of the cross-section area of the aircraft. Now, if you look at the kind of geometry, we can easily see that there are two types of cross-section that can be fit, elliptical or oval. As they are reported in this image that show the comparison of the cross-section for an oval and an ellipse. The ellipse is the red line, the oval is the blue line. You can see that ellipse can have a higher cross-section, which means higher volume. So if we apply this concept to the ICDs, we can clearly see that the cross-section in an ellipse. So we would like to fit. So the cross-section of the tank should be elliptical or spherical at least. Now, the shape of the tank also, as we say, affect the tank volume to occupied volume ratio. As we can see, if we compare the circular cross-section to elliptical section, you can see that elliptical section allows to have much more tank volume to occupied ratio, and this ratio increase with the ratio between the major axis and the minor axis. At the same time, we have some problem on dealing with the pressure because, as reported here in this analysis of deformation of ellipsoidal section of a cylinder, the maximum deformation in this type of cylinder is on the maximum axis. On the other side, the circular section do not have this type of deformation because it's much more uniform over the surface. So we need to stay low on pressure if we want to have an elliptical tank and increase the volume to tank ratio. Now, thermal insulation, how do we have designed? We have to keep in mind that we have to reduce as much as we can the thermal insulation, and at the same time, we have to reduce the mass. Now, the heat that comes from the pipes can only be reduced by increasing the length of the pipes. As for an example, has been done here by the Netherlands Aerospace Center, where the tube is not as straight, but there is a spring, which is done to increase the length and reduce the heat input. You must be aware that we have 1 watt of energy entering 4 meters of tube. So if we have just 30 meters of tube, we multiply this value by 2. So it's a lot, and if we multiply this for all the pipes that we have, we can have a huge amount. Now the heat that comes from this support of the tank, but we cannot really work on the length because it's fixed by the vacuum jacket, but you can work on the material. So if you use polyamide as reported in this case, you can strongly reduce the heat coming from the outside. And also we would like to reduce the surface contact. One example is given here. where we have used composite ring to minimize the surface of contact between the outer and inner vessel. But if you want to reduce the heat coming from the surface, there are three main insulating material that can be used: this foam, aerogel, and multi-layer thermal insulation. Thanks to NASA that did a lot of work on that, they have published some results concerning the amount of mass that is required to insulate a liquid hydrogen tank for different type of technology. As we can see in this measure, the vacuum jacket with MLE technology, which is the purple line here, allow to have the minimum mass to guarantee the same amount of heat inputs in the tank. So which means that MLE for liquid hydrogen vessel is a very good choice. Now, at the last part is how we control the pressure inside the tank. We don't want to have overpressure or a depressurization of the tank. So to avoid depressurization, we can use a pressurization gas, so which often is helium. We can return part of the gas that we are feeding to the engine to the tank, or we can use a heater. Usually, using a pressurized gas is actually expensive because we need to install a pressurized vessel. Helium is really expensive, but it's the main advantage is that simple. Return gas technology is simple, but we have to consume some fuel to pressurize the vessel. And heater, of course, do not need fuel consumption, but we have some heat leakage that can enter from the pipe from the heater, and of course adding heat when we want to keep it cool, so not to be very tight. So for us, it's better to stay to a return gas solution. Now, how do we avoid overpressurization? It's very simple. We use a boil of gas that open when the pressure is above a certain value. We can use pumping. We can use a pump that can create the same effect of sloshing inside the tank. And we can go, of course, using dry cooler. Among these solution, using boil of gas valve seems the easiest, and adding pump inside the vessel seems also a good choice, because keeping pumps inside the vessel is one of this allows them to work more efficient than outside. Now let's move to the fuel system, which is the architecture. How we the pumps have been designed, the heat exchanger, the buffer tanks, and the valves. Now, as you see, with storage cryogenic condition, we need to bring the hydrogen to the cold condition, because we cannot feed a cryogenic condition inside the internal combustion engine. The pressure that is accepted by the engine is around 40 bar, and the flow of fuel is actually changed a lot during the missions, as reported here. We start our mission with 100% amount of power, and we conclude the mission almost with 0. So actually, we have seen that there is a high compression ratio, high temperature increment in the fuel system, and the flow is variable in time. So actually, we need valves to control the flow, a pump or compressor, heat exchanger, and buffer tank, roughly speaking. So there are 5 types of architecture that can be used: liquid compressor, vapor pressurization, mixed compression, storage tank pressurization, and isobaric pressurization. Now, all these type of configuration requires different amount of equipment. There are already an example of storage tank pressurization, for example, the one used by Air Liquide, and isobaric pressurization, which has been used by Aviation. We would like, as always, to reduce the number of equipment, minimize the mechanical power that you use from the engine, and as your safety in case of mechanical failure. Now, if we consider the working pressure of the tank, the numbers of equipment, and the mechanical power, it is almost easy to understand that the better solution is to use the liquid pressurization. So using a simple pump and compression, and eventually a buffer tank, because we can guarantee the lowest value of pressure inside the tank, a relatively low number of the equipment and minimizing the mechanical power. Why? Because we minimize the mechanical power, because as we can see from a thermodynamic point of view, pumping a liquid requires less energy than compressing a gas. Now, usually the choice of the pump depends on the compression ratio and on the fluid flow. For our type of application, the flow rate is below 5 grams per second, and the compression is around 8 to 1. So which means that we have to use piston pumps, as the report in this graph, which are really suitable for very low pressure, so very low flow rate and high pressure ratio. There are different examples of existing pumps. For example, one of Toyota is used, but this type of pump is very heavy and big. The compression chamber is directly submerged in the liquid hydrogen, but the motor is outside, which actually is not very suitable because there are a lot of inputs to the system. What you seems most promising is used a magnetically activated pump, for example, someone from a scan pump from Petri Tech, or using the one from cryo pumps from EICLHAIR Dresden. Anyway, these type of pumps are really expensive. They are still prototype, at least for the German technology here, and they must be tested in aircraft environment. Now, the other main units is the heat exchanger. We would like to avoid the phase change of the heating fluid. There is, as said, a big temperature difference, and we want to use a fluid that is available on the aircraft, so air, exhausted gas, or cooling water. Now, if you look at this table that synthesizes the main drawbacks and advantages of using each fuel, we can easily see that air is largely available, but very depends on the altitude, the weather condition. We cannot go below 10 degrees Celsius. Exhaust gas a little bit hotter, stable on temperature, can be a good solution, but if we can affect the running of the engine. And then you have the cooling water, which is actually at the temperature between 19 and 100 degrees Celsius. You can go up to minus 38 degrees Celsius if you add some glycerol. And if you do some rough calculation, we need 19 kilowatts to bring liquid hydrogen from minus 153 to minus 20. So if we do roughly some calculation, we need 1.3 kilograms of air, which is a lot. The exchange can be done with exhausted gas, but if you use cooling water, we can really see that we have a lot of water we can reuse for heating up the liquid hydrogen. So we think we can use that solution, use the cooling water with glycerol. Now, the most simple configuration, we would like to have a simple configuration, because simple configuration means simple manufacturing, and we would like to minimize pressure drops. The solution that we use is actually a heat exchanger double pipe counterflow, where the liquid hydrogen flow in the inner pipe and the liquid and the heating fluid flow on the external pipe. We have some roughly calculations show that with 45 centimeters, we can do the heat exchange, and we don't have cold spot. How we have sure that there are no cold spots? Because we have calculated the temperature profile on the cold side, so where there is a liquid hydrogen, and on the hot side where there is the cooling water. As we can see, the freezing point of the heating fluid, which is indicated here in this line, has never reached. And as you can see by the temperature profile on the cold side, 45 degrees Celsius, 45 centimeters can really make the heat transfer. Now, buffer tank, why we need buffer tank? Because we need to smooth the variation of the flow on times. We need gas for starting the engine. And if for some reason the pumps do not work, we need some hydrogen to running the engine and to assure the function of the aircraft. Now, if you increase the pressure of the tank, we reduce the volume. So that's what we want, but at the same time, we increase the volume of the tank. Now, this is not what we want, so we need to optimize this parameter to have compact and optimized pressure buffer tank. Example of small size of pressurized hydrogen gas tank. I report, for example, here from Suzuki that are developing hydrogen motorbike. As you can see, the same tank can be used also as buffer tank for our system. Now, as you can see here, there are different curves represent showing the mass of the tank as function of the operative pressure for different times of using the tank without feeding. As you can see, if you increase the time that you use the tank, we have to increase the mass of the tank, so we need more pressure, so more mass of hydrogen. As we can see, but it's hardly to see, but there is a minimum value around 200 bar to minimize the pressure. Sorry, minimize the volume. And if you see on the left, there is the behavior of the thickness of the wall. As you can see, we can find again a minimum as function of the pressure due to this due to the way that we reduce the pressure. So we reduce the volume. So we reduce on somehow the effort on the material, but at the same time, increasing the pressure means we bring more effort on the tank. Now the valves, they are another important element of the fluid system. For the gas part of the fluid system, small scale valve already exists for hydrogen, and they can go up to -50 degrees, easily to -50 degrees. On the other hand, if you need valves for the liquid hydrogen part, so the cryogenic part, is hardly to find, and maybe they do not exist. Cryogenic valve that can be used for on aircraft that has small size. These are some examples used on Toyota. As you can see, we talk about valves that have a mass of 1.2 kilograms. They are very, the length of these part of the valve is around 70 centimeters, so it's really hard to fit on a small aircraft. So on that part, we have large valve, almost watertight, EV, and expensive, so we need to find a new solution. Now let's move to the conclusion of the presentation. So we have seen how these, that even if the aviation do not produce so many carbon dioxide emission, we need to avoid as we need to change the use. We need to use hydrogen for the aviation. We see that the fleet is very old, and liquid hydrogen can be used as a fuel. We have seen the phenomena of the liquid hydrogen that affect the design of the tanks, such as heat transfer, self-fertilizations, thermal certification. We have seen the structure of the tanks, the architecture. We see there are no rules for designing the tanks. We see how to deal with the operative pressure, how to optimize thermal insulation, and see how the pressure control is designed. And the first system, we have seen the architect, so it's pipe pump, heat exchanger, buffer tanks. We have seen that the pump was already existing. Its transfer is not so complicated, but the main point, critical point, is the valve. So if the main point that should be remain is the use of liquid hydrogen with IC with internal combustion engine is a very good solution, can be a very good solution for light aircraft. We must be aware of the pressure variation inside the tank and the fact that the liquid hydrogen always evaporate. We must keep in mind that the pressure must be kept as low as possible in the tank to use different shapes. Thermal insulation must be optimized to reduce the mass, and return gas can be used for controlling the pressure. The fuel system, as we can see, the main problem is valves. How we can design the valves that can be put on aircraft. Also, the perspective with Roger main testing the valve, manufacturing the tank, and running some tests on heat transfer. Develop small scale valves for cryogenics, and testing the tank for testing on pressure the tank for an elliptical section. Thank you very much for your attention.
Wow. Absolutely amazing. I hope you all can hear me okay. I was having some audio issues. Do you hear me, Nicolò?
Yes, I can hear you, Danielle.
That was such a huge contribution to the hydrogen aviation ecosystem. Thank you for the good memories. It's been a minute since I've seen first law thermo equations. And we've got a lot of questions in the chat. But I'll start just kind of breaking the ice. Did DTC develop the tables and equations and charts, or did you sort of find them in several locations and put them together? I'm wondering if there's a consolidated place where I might be able to see and do some examples. I could see that being valuable.
Um, we have used some works for NASA because they have the main source for this type of project. Then the design of the process diagram, the design of the tank, and the choice of materials, choice of type of thermal insulation is something that we have done on by ourselves. Uh, our design has not been approved by an external company. For a simple question, we are not sure that this, because this is a really sensitive technology. Uh, so we prefer not to share the I would say the real details of our technologies on to another engineering office.
Sure. Well, I'm surprised you shared as much as you did. I mean, it was fantastic. So, I mean, I think you guys are in the position to potentially lead the onboard storage of hydrogen aviation. And perhaps I was thinking as you were doing your presentation, are they an NGO? Are they doing this to advance the knowledge? But obviously, there's something more. If you're, not doing this as an educational reason, there's something more that you have that you're not sharing. Would that be a correct assessment?
Yes, yes, I'm sure something that it can be, as you can say, it can be useful to understand the problems that we have, the to share the approach that should be used. Of course, anyone is free to use a different approach on designing tanks because, as as you have seen before, there are not defining rules for liquid hydrogen tanks for aviation. Something exists for land vehicles, but today there is a standard for aircraft.
Yeah, that's something that we're working on as well. Do you see DTC being part of that standard making process? And if so, then I would love to have future conversations. That's something HYSKY is very interested in putting together throughout the next year and bringing on folks that have technology that's at a certain TRL level that can help guide the rule makers.
With pleasure. We think that the first one that will have a strong and efficient technology will set the rules for the others.
Yeah,
And
I
I think
agree.
so. That there are some case studies, as we see in the Air Liquide. There seems some working project for Aviation. There are companies that works um, on aircraft. So I think the first one that comes with a very efficient technology will set the standard for the other.
Hmm. Yeah, I agree. Okay, let's get to some of the questions. There are several in the chat, but I am going to call on folks in the order that they came in. I don't want to ask the questions for you because I usually butcher them. But Adam, if you are still on, feel free to unmute, turn your camera on if you like, and ask your question.
Hey Danielle, this is Adam Flanger from NASA Kennedy Space Center. Thanks a lot for that great presentation, Nicolò. No, I really just had a comment back in the beginning when you were talking about the benefits of fuel cells versus internal combustion engines. I had heard through the grapevine too on the few folks that are working on ICE hydrogen engines that one of the nice things is that regardless of how long you run them, everything stays pristine inside of it. So there's no carbon. So there's no carbon buildup on anything. There's the oil basically stays pristine. So we can also say that from a maintenance and longevity standpoint, that might really have a lot of impact.
Exactly, is one of the reason why we have chosen the sparkling engine is because the architecture is almost similar to the one that we use on a gasoline car or gasoline aircraft. Piston, cooling systems are almost the same. Oil system, lubrication. Yes, of course, you have to change some parameters. For example, you have to be sure that the oil that you use is suitable for hydrogen, because hydrogen is a very small molecule. It can attack oil. You have to be aware of leakage, so you need some joints that they are suitable for hydrogen. You may be aware of hotspots. I know that because hydrogen has a lot of heating value, so the temperature in the chamber is higher than the one that, if I remember well, is higher than the one that you have using with gasoline. So there are some technology in the system to reduce the temperature in the chamber. I know that some manufacturer of hydrogen sparkling engine, they use, for example, water. They inject some water in the combustion chamber to keep the temperature low, to avoid hotspots, which also produce NOx. They know that they use some materials with a very high conductive properties, again, to reduce as much of heat from the combustion chamber to avoid overheating and NOx production.
Awesome. Thank you for that. And I'm very grateful for this slide. I think I say every day that there are two ways to use hydrogen. You can burn it or you can use it in a fuel cell. And I just wrote kind of a big rant because I saw somebody write an article called hydrogen versus electric versus SAF. And it made me cringe because, well, depending on how you use it, was assuming that all electric was battery, and that all hydrogen was not electric. So thank you for this slide. This is a perfect example of what I've been saying. And this is also a good time to point out. So Doug Starfield had a comment about power density. And Doug, you're more than welcome to unmute. I don't want to get too much into the weeds of deriving kilograms per kilowatt, but it does come down to what I was saying in the chat. Doug, would you like to unmute and make a comment about the power density units?
Well, usually, yes, thank you. Usually for fuel cells, the membrane area is referenced for power density. So that's why this looked kind of, it should have been watts per, some unit area. So that's all I was trying to get at there. You just want to compare apples to apples and get the right unit.
I'm sorry, I didn't hear your question. I think
If
there's
you,
some trouble on the
if
audio.
if you scroll up in the chat, you'll see it. But his comment was power density is usually watts per area. That's his comment, but that's not what I've
Okay.
usually seen. Yeah, but do you want to comment on that?
Yes. When I searched some value, I found there are different way of defining this property. Of course, you are free to say the opposite. I found some values I think that is really representative of what we need on our aircraft. We need something that is light and powerful. So I searched value for kilograms divide power, and to give you that idea of light and powerful. That's what we want on our aircraft. And today's standard, the first day today, they do not they are not enough light and powerful as on sparkling engine. But
Thank
I know that
you.
they are working on fuel cell that can be compared to sparkling engine.
Oh, good. Oh, thank you.
Scott, would you like to come on and ask your question?
Yeah, thanks. It's relevant to this part as well. So it was really coming back. This is the first time I've really seen this direct comparison between these two. And I'm not sure if you're taking into account the heat losses and the energy losses within it. And I was always under the assumption that the fuel cell was more efficient from a total kilograms of hydrogen needed to the output of work, in this instance, driving a propeller or a wheel, or at the crankshaft level in the ICE. I guess it's not a direct comparison to the kilowatts produced out of a fuel cell to then go into an electric motor, but is there a way that that's one-to-one comparison between, like, at the work level, at the propeller or at the wheel, between these two?
You're right. Fuel cell are more efficient than the internal combustion engine. We didn't push the study up to understand how much power we have at the wheels, because we were looking much more on the, as you can see, on the ratio between mass and power. But of course, fuel cells are more efficient, so it means that they produce less heat than an internal combustion engine. If I properly remember, something like 40 and 60% of the energy coming from hydrogen is lost on heat for a sparking engine, something like this, and for fuel cells much lower. So of course, efficiency, I think that will play an important role, because if your system is very efficient, that means it can increase the real power produced, and this will be a very important parameter to keep in mind on choosing this two type of technology.
Thank you. I had the next question. It was on your equations when you were showing what the mass of there was one variable okay, yeah. What was the last, what is mHell, which is a funny, I didn't catch that one. My audio cut out.
ML?
MHELL. I don't know if that's what you called it, but it's bottom of the equation to the right, where the arrow's going down, where the mass of the liquid, the LH2, what was
sorry, the hill.
Okay,
Here?
thank you. Yeah.
Yes, because we cannot use all the liquid hydrogen that we have in the tank, because some of or part of the liquid hydrogen must be kept in the tank to keep it cool, to keep that cryogenic temperature. If we remove all the liquid hydrogen, as we have seen before, due to the heat inputs from the environment, the gas that remain will become warm and warm. So if we left an empty cryogenic tank or an empty liquid hydrogen tank, after some day, the temperature inside will be, I don't know, anyway, it would go close to the temperature of the environment. And
Okay,
if you
gotcha.
want if you want to run we have to pull down the tank, which actually takes time. So we have to first keep liquid hydrogen inside to keep it cool.
Got it. Thank you. Thomas, you were commenting on the book. Have you seen this? Oh, this is your book. No, this is not your book. Sorry. Have you seen a book, Cryogenic Engineering, Revised and Expanded by Thomas Flynn? There's a link in the chat. I'm curious if you've read that or used that as a resource.
I've heard about it, but I didn't have time to read it. We have used some advice from this book. We have used some articles coming from cryogenic engineering for Springdale, I think. But I didn't have the
Cryogenic
pleasure
engineering,
to
yeah.
read it.
Okay, very cool. Sant, you're up. Hi, Sant. It's good to see you. Let's see, is Sant still with us? I don't know if Sant is still here. I don't see his name, but his question was, can the tank be irregular shape? And I think this was when you were talking about the ellipse and oval. And there were many replies. Thomas said, sure, but you lose significant thermal advantages of spheres or cylinders. I asked Thomas if he was with DTC because he was answering some of the questions. Do you agree?
That's another important parameter. Shapes control the ratio between the surface and the volume of the tank. If we can reduce this ratio, you can reduce the input in your system because you have a large amount of volume, less surface. And if we use a shape that's different from a sphere, we increase this ratio, so we increase the amount of surface per unit of volume. Now, this is another parameter that should be taken into in the designing of the tank, because if we increase the surface, so we need more insulation mass, which actually may be balancing out the increment of the tank volume. We have considered this parameter, but we didn't show on this presentation because I think we didn't have enough time to see this the influence of this parameter on the design of the tank.
Awesome, thank you. Wade, you're up. Would you like to ask your question?
Oh, yes. So just yesterday, in fact, I saw an article that was published on Thursday. The EASA, European Space Agency, has a project called Phoebus, but they're trying to replace their metallic liquid hydrogen tanks with 2,600 carbon fiber reinforced plastic tanks for the Ariane 6 rocket. So I was wondering if you were familiar with that project.
We are not very familiar with project. We have heard of another project, which was on joint venture between an Spanish research institute, but they are trying to manufacture liquid hydrogen tank by printing it by using 3D impression. They know that they failed to keep the pressure inside the tank, so they're still working on the process on the material to use. Of course, if you can use a composite plastic, it's much say lighter than aluminum and stainless steel. But the point is, how can we avoid fossilization of the plastic? Because one of the main problem is the temperature is so low that the glass transition of the plastic occurs, and the plastic behaves like glass. So if it takes some vibration, some say impact, it will break like a glass. So this is something that we don't want on a cryogenic tank.
Okay.
Any leakage of liquid hydrogen is a huge problem for the safety.
Okay.
Also, hi, Wade. Good to see you.
Good.
Wade is
okay, thanks.
Yeah.
You're welcome.
Great to see you, Wade, as well, always. Next we have Bill Nye. I don't know if it's the science guy. Bill, would you like to come on and ask your question?
Yes, I would like to ask a question is the price first. I'm not sure how much the cost at the same mass volume or mass weight between the liquid hydrogen to the Jet A. That's the first question. Second question is the safety regarding the transportation and storage. And the third question is about aircraft jettison condition when we try to release the liquid hydrogen in the air. What kind of device it is and how safety it is. That's the three questions I have.
Okay, concerning the cost, I think that today manufacturing a carbon fiber tank for compressed hydrogen is cheaper than manufacturing a cryogenic vessel for liquid hydrogen. And if as we want to do or use elliptical cross section, it will be much more expensive because there are prototypes. There are not so many people that manufacture cryogenic tanks, so less people can give service. That means that the service price is very high. Concerning the certification, is well understood, is how we deal with the Jackson of the liquid hydrogen. This is a very I don't know if there are studies showing what is the impact of liquid hydrogen in air, but let's imagine something that is really cool, that is and its temperature is below the saturation temperature of the nitrogen, which means that it's so cold that it can be instantly liquefy air. At the same time, the liquid hydrogens want to go back to gaseous state. So it will absorb very quickly heat and it will expand at the same time. So we may expect that if we check in some, if we withdraw hydrogen from the tank and we liquid hydrogen from the tank, we put it on the air, we expect a huge cloud that's forming, which expand really fast, and at the same time the environment around it will formation of glass that can be projected, liquid air that can be liquefied. Nevertheless, we don't forget that liquid hydrogen want to react with the oxygen, so we may create a very explosive environment around the jet of liquid hydrogen. So I don't have the answer. I don't know how we can deal with it, but I may raise a question: do we have to do it, or another choice would be to maintain the liquid hydrogen inside the tank?
Very good question. Thank you. Stefan, you're up if you would like to ask your question.
Yeah. Hello, Nicolò. You can hear me? It's okay?
Yes, I can hear you.
Okay. Hello. Just a question. You presented a quite interesting gravimetric index, about 35 to 45%, if I remember well. Can you tell us what is taken into account in the mass of the tank you consider? Is that only the vessels, or do you consider also the pumps, the valves, and all the, I would say, the needed hardware as to make it work?
Okay. We just consider the vessel and the equipment that are installed inside or on the vessel, which means valves, piping, maybe pumps, or the other part of the fuel system, such as heat exchanger, the valve to control the flow. The buffer tank we do not consider this calculation. Just consider just the mass of, or our parameter, just the tank.
Okay, thanks a lot. Thanks a lot for the details.
You're welcome.
Thank you. Next up is M. Krish. If you're still here, I'm sorry, that's how the name shows up if I'm not saying it correctly.
Oh, no problem, no problem. Now, my question was, I think, what material are these tanks made of? I think it's a basic question. Maybe I missed it.
The materials.
Yes.
Okay. The materials is aluminum. There are different type of aluminum that can be used. I will not say what we have decided to choose, but it seems that aluminum is something that can guarantee is actually behave quite well at the cryogenic temperature. We have seen an increment of the mechanical property that is higher than the stainless steel. I know that today stainless steel is being used for manufacturing cryogenic vessels for the same reason that is easily to weld, and a lot of a big part of the manufacturing of this type of tank is made by people. So stainless steel is chosen is often used, but we prefer to use aluminum.
That's basically aluminum with a lot of insulation on the outside.
Yes, the insulation is we use a multi-layer insulation. because we have seen that is a standard, and as you can see from literature research, this type of technology allows you to minimize as much as you can the mass of the insulation with respect to the foam or aerogel. The external, the vacuum jacket, on the other way, is made of composite. They decide to use composite to reduce the mass of the tank.
Okay, and then I saw the 1,000 euro per ton hydrogen. That's your today's price.
That's the price. Sorry.
That I saw in one slide about $1,000.
Yes,
1,000 euros.
This is the price of the fuel. If whether we're, oh yes, this is the price of the fuel. Let's see, just as you can see, this is the price of the fuel. Shaft are usually more expensive than hydrogen, and Jet A is the cheapest.
Right. Yeah. Right.
Because it comes from fossil fuel, and all the other hydrogen and SAF, they are product, actually a quite expensive product.
Okay, so you are using 142 euros per thousands of joules per kilogram, right? That's what you're saying.
Yes, sir.
Okay. Okay. Thank you. Thank you.
You're welcome.
Great question. Thank you. Next up, Anurag. This will probably be the last question. There are many more questions. Unfortunately, I don't think we'll get to them all. But Anurag, go ahead and ask your question.
Well, hi, Nicole. Thanks. A wonderful presentation. And my question is simple. I need to spend a few more hours on this. And how can I get the privilege of doing so?
Well, I can answer that one. Well, I will upload this video and the slides into HYSKY Connect. So those of you that are asking where you can get the slides, just go to connect.hysky.org. It's free. Create an account and they'll be in there later today. Nicolò, huge thank you for this presentation. I want to follow up with inviting you and your team to attend Flying High and possibly speak at Flying High. This was a absolutely fantastic presentation. So thank you so much for spending your evening with us. I think we watched the sun go down with you. So yeah, just huge thanks. Really great job.
Excellent.
Thank you very much, Danielle.
And thanks, Danielle, for hosting this. This is just excellent.
Thank you so much, everybody. Nicolò, I'll follow up with you on getting you some passes and see if there's interest in speaking at our event on November 5th, where we'll have 300 people. So thanks so much again to the DTC team, and have a great week, everybody. Bye.
Bye-bye. Thank you very much. Bye-bye.
Thank you so much.